I'm Apratim. I'm part of the gravitational wave group here at IUCAA. Currently I mostly contribute to the LIGO Virgo Kagra collaboration. In various aspects of data analysis, but mostly applications to tests of GR. But I also contribute to the different search and the parameter estimation pipelines, mostly the parameter estimation pipelines. Also, for the LIGO India project, right now I'm just doing most of the organizing workshops in different parts of the country, trying to bring in more people into the different aspects of the gravitational wave science, which involves not just the physics and the astrophysics, but also the instrumentation science, detector characterization, and various other, so calibration and all these things. So these are actually what, like instrumentation science, detector characterization, these are the things that we are looking for more people. So as LIGO India comes into, becomes live, this will be quite important. But in my previous avatar, I was a relativist. And so to keep it alive, I still try to work on various theoretical aspects, mostly on gravitational wave memory effects, collapses. I also work a bit on neutron star modeling. Can we constrain dark matter fractions? If we have a model where it's a combined, it's not just a neutron matter, but also a combination of neutron matter and dark matter. So I kind of try to do multiple things. But the main idea of this set of tutorials, the 5 tutorials that I'm planning to give is, how many of you have used xAct in your life before? I know you have. A couple of. That's great, because less the number, better it is. Nobody to challenge me. So the idea is, in the other tutorials, you will be asked to do a lot of calculations. And I want to be this nice relative in your family who gives you a lot of gifts, and I don't know. It's good or bad, I don't know, but that we will see. But the idea is to that if you face all these problems, and anyway in your life, when you're trying to, I heard many of you are working on various aspects of modified gravity and other theories, other sort of aspects. Is it possible for you to use this package to do your work? And hopefully I think it can be, and that's the main idea. And if you can spend some time learning this, if you're doing very simple sort of tensorial calculations, this is not required. But I am guessing all of you are into more involved sort of, doing something more involved, and that's why this might be quite important for you guys. So I had sent out tutorial 0, which is mostly about how to install xAct. So I'm guessing everyone knows mostly what Mathematica is. But if you have Mathematica, you can now install xAct. As I had mentioned in the tutorial, which I'm not showing here, but as I mentioned in the other tutorial, and I can pull that up as well. Right. So what you need to do is, depending on which system you're using, you have to just download the tarball or the zip file, depending on whether you're using a Unix-based system or Windows, and you need to just place it. I'm just considering that you are just a local user and not a global user. You just need to put it in this applications directory here, the untarred xAct directory. If you can just put it, it should work. How many of you have tried it here? It has worked for you guys, like the basic check. It has worked. Okay, great. So I'm guessing it's working, so we can move ahead. The other thing that I wanted to point out is this is none of the things that I'm going to talk about is my, like it's not genuine, like it's not my thing. It's mostly I've taken it from other resources, and most of the resources can be found here in this xAct page. So just to point out, there are this 4 important packages, but we will be mostly working on this xTensor and xCoba, but this is built on this 2 other sort of programming, some packages which are the xCore, which has sort of the basic, which has nothing to do with GR. It has a sort of the basic computational tools which are required, and xPerm is some sort of permutations, manipulations of the large group of permutations, which are used by xTensor. So xTensor depends on this in these 2 packages. xCoba depends on all these 3. So these are the basic things that you have to install. If you are taking the entire thing, you can individually install this, but if you are using the complete tarball or the zip file, then you will be able to, then all these things will be installed anyway. The other important thing is if you are really planning to work in various aspects of tensorial calculations, you should go through this documentation. Now, okay, the first part is various tutorials and tutorial videos that you can find. And you might choose whatever you think fits your work. But the most important thing is you can look at the documentation of xTensor and xCoba. So today we will be mostly talking about xTensor. So you can look at the documentation of xTensor. Now this is quite extensive, but it will be good to spend some time on it if you can. Right, so what I have tried is to introduce some of these tools. This is not obviously exhaustive. Any questions before we start? Great. Okay. So the documentation and the reference notebooks are given here. I will send out this notebook by the end of the day. So as I initially stated how you can install the packages. So this is how you just load the xTensor package. Any problem you find at any point of time, what you should do is just type quit and delete disable, go to evaluation and just click on evaluate notebook. Okay, so if this is already, if you have already loaded the package, you should see the different versions and everything. Now, I have just, I just told you that xTensor depends on xPerm and xCore. So this just tells you what are the different packages xTensor depends on. And as I said, this xCore is just a generic programming tools and nothing to do with actual GR tensorial calculations. And xPerm, what it does is does this computations with large groups of permutations. But for us, this is not really important. xPerm, it's written mostly in C. But if you're really interested and want to change some of these things or contribute to the xAct software package, please go ahead and look at it. Now, documentation, so this is like a normal Mathematica syntax. So you can just, if you want to know all the tools or functions which are available on xTensor, you can just type a question mark xAct xTensor star, and that should give you all the different functions. And a short sort of summary, whatever you want, a short sort of summary you can get by just clicking on whichever you want to. And so for G delta, which is this generalized delta function, you can get like a small sort of, like you can get what is the syntax of it for a G delta. But obviously this is not a substitute of the actual documentation. So if you really want to know what it is, you should go and read the documentation. I should actually briefly just open the documentation for you. So it's quite extensive. And you have this different chapters in the documentation. So if you just click on whichever you want, you can see the different, the entire notebook for it. So it will be good to actually go through it, because once you go through it, you will be saving a lot of your time, and I can guarantee that you will be saving a lot of time. So anyway, so the first thing that we need to do is you define your manifold. Now, whether you want to define a 3-dimensional or a 4-dimensional manifold, you use this particular function called, or tool called def manifold, and you can look up what it is, and you will get a bigger sort of summary here. But essentially what it says is you give a name to your manifold, and you can actually define multiple manifolds and calculate products of different manifolds and all these things. But here I'm just defining one manifold, and here is the dimension. And again, if you are working on higher dimensional manifolds, this is also something that you can use, right? So you define you give the name of the manifold, the dimension of the manifold, and the sort of indices that you're going to use. So this is something that, I've just given 4 indices here, and I've later realized that that's not the right thing to do. I should have given more indices, but these are the indices that you're going to use later. So it's better to define as many indices as possible. So once you do that, it tells you a couple of things about how that you're defining this particular manifold, which has this name M4L. M4 is basically, M is manifold, 4 is the dimension. L is just because I'm using Latin indices. You can use Greek indices if you want, which I've also defined here. So there's nothing, no problem. If you want to differentiate between Greek indices go from 0 to 3 and Latin indices go from 1 to 3, you can define your manifolds accordingly. And what it does is it also defines the tangents to the tangent vector bundles to these manifolds. Okay, so it defines the tangent space as well, which is given by this tangent M4L. So you will see this later as well. This last sort of in the naming convention, the last sort of letters give you either, depending on the manifold that if it's associated with the manifold, it gives you the name of the manifold. If it's associated with the metric, it gives you the name of the metric. If it's associated with the covariant derivative, it gives you the name of that covariant derivative. Okay. Here we have defined the manifold as M4L, so the tangent space is defined as tangent M4L. And as I said, you can even define Greek indices, and you can ask like what this manifold is, and it will give you some idea of, it will tell you what it is. It's a manifold, it's of dimension 4 and all these things. And this is your tangent space. So this is the output form of this, of the same tangent M4L. This is just the output form of it. This is the input form of it. I'm guessing all these terminologies are something that you have heard of from a Mathematica point of view. Okay, so now as I've defined two manifolds, I can just print them out, and these are my two manifolds. As I said, I can define products of manifolds and all those things, which I'm not getting into right now. The next thing, as I said, is the vector bundle. So we have already created a vector bundle, or it's being created for us. It's given to us, and this is this tangent M4L, and I can again try to ask what it is, and it gives you a set of output. It tells you it's a vector bundle. These are the indices which are defined, and the dimensions and everything. Okay. I just wanted to also point out this, the indices are called this abstract indices, and it's not so important. You can also, like if you want to get a verbose of this different, like either the manifolds or the vector bundles or the indices, the different objects, you can try to just ask for it. Okay, and now as I had only defined this ABCD in the M4L manifold and alpha, beta, gamma, delta in the M4G manifold, these are the indices which are printed out. Okay. Okay, so once we define the manifolds, the next thing that what we want is to start defining the tensors. So I'll start with vectors, and this is how you define the tensors. Def tensor tells you whether if you want to define a tensor, this is what you use. I want to use a 1, 0 or a 0, 1 form. So indices without which are positive are the 1, 0 form, so the contravariant one, and the minus a are the covariant one. And that's again, this is not important. So if you now, after you're defining the tensor, when you are actually going to use it, you can just use it like this. And as you see, it will tell you whether it's a 1, 0 form or a 0, 1 form. Now you can move ahead and try to define 0, 2 or 2, 0 forms as well. But the only thing is, here you can also define additionally whether these tensors are antisymmetric or symmetric in the indices or not. So for example, here I have defined a tensor sorry?
That tensor should be closed. Oh, yeah.
Yeah. So I have defined a tensor of the form 2, 0, which is antisymmetric in its indices, and do remember it. So I just want to write it down. Because I will use this later. This is an antisymmetric tensor, and then I define something as a 0, 2 form which is symmetric. Okay. So again, when you're actually going to use it, you can use it in this way, and you can see that whether it's what sort of tensor you have defined. Okay. Any questions till now?
If you don't define will it be taken automatically as symmetric or
If you don't define,
anything?
it's going to be, I don't think anything gets defined, or maybe I'm wrong. Please find it out. This is one of the questions. Okay, so I can also define a mixed sort of tensor, and so this is how I'm defining it. Now, you can explicitly write something. So if you want to write a metric tensor, you can just write this here. You can write it as metric, and you can say that, okay, print as G. Okay, that is also a notation which works. Okay, so the other thing is, if you want to not use this tensor anymore, it's better to delete it, or if you want to redefine it, it's better to first undefine it. And this is what this undef tensor does. Okay, and it's not like you can just define tensors or vectors. You can also define constants. So if I want to define a phi, which is a scalar field, in the same, sorry, just the one more thing that I wanted to, yeah. So remember, you're defining this tensor in this manifold, so that should always be mentioned. Now, so you have a scalar field, so obviously you don't have any indices, and you're defining it on this particular manifold. But you can also define a constant scalar field, okay, which essentially means is you don't need a manifold to define it. So its derivative is also going to be 0. And you can obviously define symbols, constant symbols. Right. So given this, let's try to define a metric. And obviously what we are trying, some of you might have used some version of gR tensor before, I'm guessing. So there you actually define the metric, and you get whatever the Christoffels, the Ricci, and the Riemann, and all these things. As I said, if you want to do something simple, then it's fine. You can use those things, but this is more about symbolic computations, right? So so in principle, at the end, in the next week, I'll show you how you can. I'm sure during the lectures or during any of the other tutorials, the resource persons or the lecturers are going to show how you can vary the action to get the field equations in GR. Now, if you can set things up properly, you can do it. By that I mean, given any action, you can get the field equations. So you don't need to really do the calculations by hand, but it's always good to do the calculations by hand once to get a feeling of it. But you don't need to, if you're working on in different alternative theories, you don't really need to do these calculations every time. This will, I'm hoping, will save some of your time. If you want to if you're looking into black hole perturbations and black hole stability, and you want to perturb your system, there are tools to do that. Okay.
And you will just put the action here and it will solve the problem. Are you going to share that notebook?
Yeah, that's the plan. Now that I'm thinking, if people are so interested, should I make the. So, one of my students is sitting here, so I generally tell them to do it. So they learn all these things on there, or they copy it from somewhere, whichever works. But yeah. So yeah, so that's the main goal. Like if you are even from a gravitational wave point of view, we are very much interested in waveform modeling, and this requires this thing called a post-Newtonian formalism. So the inspiral of the waveform can be well modeled by the Taylor expansion of your V over C, right? So the velocity is not as relativistic. By the velocity I mean the orbital velocity is not as relativistic, and we can use this sort of Taylor expansion. And this is up to the first PN 1.5 PN. The calculations are tractable, and then it's become extremely difficult. And there are very few groups in the world who does such things. In India, Professor Bala Iyer was one of those. But now there are very few people who are working in this direction. So if you are really theoretically inclined, this is one thing that you can think of working on. But again, you need tools. You can't really do all these calculations by hand. You need to learn these tools. And there are people from the post-Newtonian groups who have actually developed an offshoot of this, which is called an XPPN, which is the same thing as parameterized post-Newtonian. And so you can, in principle, also contribute. If you have done something and you think this needs to be contributed, you can also contribute to the xAct package. Right, so let's move on. Let's try to define the metric now. Again, I hope now you already understand what this is. So I'm defining a metric G with two indices which are downstairs of O0, 2 form. And my signature of my metric of the determinant is -1. So it's a -111 signature. And what I'm defining here is a torsion-free covariant derivative. So this gives you a connection. I heard in the first lecture by Patrick, he talked about, I think he was talking about Cartan, and so you can look at, so maybe you can take up a problem of how, like here what we have defined is a torsion free. So you can take up a problem where there is torsion and try to get this, get the field equations for those. This is one of the tasks my student has to do, but if you can help him, that will also be great. So once you define the metric, it gives you for free a lot of other things. For example, as I said, it will give you the symmetric metric tensor G, but it also gives you the Levi-Civita tensor. And again, as you can see, this naming convention is such that at the end you have G. So if you had given the metric name as metric, it would have been epsilon metric. Okay. So the covariant derivative is defined here, and it says that it's a vanishing torsion tensor, and that's what we expect. It also gives you your Christoffel, the Riemann, Ricci, the Weil tensor, the Einstein tensor. So you get everything for free once you define your metric, and this is just a symbolic representation of all these things. So given, if you actually define your metric, you will get the corresponding, whatever you are looking for, you will get them. Okay, this is what GR tensor or any other sort of variations of it used to do. Now at the end, you see this weight +2. I think this is if your signature is minus plus 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 minus yeah, plus 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 plus, this is just giving you this plus 2 density out of that. Right. Any questions till now? Okay. Everybody's understanding. That's awesome. Okay. So now we want to use this and try to figure out whether everything is working fine or not. I defined an antisymmetric tensor. So essentially what I'm doing is, yes.
So your that rotation depth metric that you are defining.
Yeah.
This is computing all these things, right?
Yeah.
Can we just print it?
Yeah, we can. We will come to that. At least some of those we will see. Yeah, as I said, when you print it, it will just give you a symbolic representation of it, right? So you can do all the symbolic computations.
Yes.
So now if you define, So now you define the metric, it will give you the, So we will come to that, yes. So right now we are just at the stage that we are just doing symbolic computations and nothing else. Okay. So what I want to define here is V, VA, VB or something else, yes. And say 2 canonical is something which is simplifying. You know the this operation of simplify or full simplify in Mathematica. This is just somehow some sort of that. It does a lot of other tensorial sort of simplification, and it gives you this. Can anybody tell me why? Okay, is this clear? So it's working. Okay, so if I am defining, so I'm just trying to, today it's more about the feeler. So I'm trying to give you a feel that if you can write things down properly, then some of the simpler operations that you have in your mind, you can test it out. So if you want to look at, can I do this Bianchi identity, and is it giving me all the results properly, I can try to do those things. So I have written some challenge questions in the notebook itself, but if you find something that you want to try out, do try out. Okay? Right. Similarly, I have defined another thing. If this is this should also be 0, right? Okay. Yeah. So, but if I have this should be what? Again symmetric, so there is a minus sign which will come out. Are this clear for you guys? You know much more than this, so I don't want to. Okay. Okay. So yeah, I think these are things that you understand is an odd number of tensors, so it goes to 0, the last one.
No, I think there is a problem.
Is it? Oh, sorry, this is minus P.
Yes.
Flip, yeah, sorry. So,
Actually, you have written the other way around. F, A, B, upper A, B. That is fine. The same.
yeah, sorry. Just, it doesn't matter,
Yeah.
but let's be consistent. Right. So you can even check. So I'm not. I hope you understand this as well. But you can. You don't understand? You should figure it out. This is your challenge. You should figure this out. Yeah. So, but the other thing that I wanted to say is, even if you're not writing things properly, you can actually use this tool called validate to figure out where you're going wrong. Okay? So for example, this is a good enough, like saying this is fine, right? Writing down this is fine. But this is not. You might make a mistake while you're writing down all these things. You're busy working. You might write something like this, and you don't know where things are going wrong. So if you use the validate tool, it's going to tell you what is the mistake that you're doing. Okay? Right, so if it's all fine, it will give you the expression, but else it's going to give you some sort of error, and here you're going to get a null response. Similarly, I tried this for a tensor as well, not just for a vector. And similarly, if you have this sort of repeated indices here, it will give you an error, right? So now coming to your question, I want to write down the Riemann tensor, and this is basically the syntax for Riemann tensor. Again, the final, this name is going to change depending on what is the name that you give for your covariant derivative, and that's here. Now, I defined, this is not important, I just defined two more vectors because I will need it later. So I wanted to write down this particular quantity. Okay. Now, can anyone tell me why, if this quantity goes to 0, like, so I've written the same thing, just two canonical, so it actually does the simplification and it goes to 0. Can anyone tell me why that is the case? So when I'm getting the Riemann tensor as for free, it already defines the properties of the Riemann tensor, right? So can you tell me what is the property which is being used here? Huh? Yeah, but what is the property which is used here that this expression goes to 0? Riemann tensor is what? You guys did not do anything of this sort yet? You should not be responding.
R, A, B, C, D.
Huh.
If two indices A and B are equal, then the Riemann tensor is 0.
A and B are equal. Where A and B are equal here? Also, why that should be 0? Why?
Oh, sorry.
You remember why you came back from South Africa?
No, sorry.
Anybody? Properties of Riemann tensor.
Interchange of first two and second last pair. That gives you an antisymmetric.
It's antisymmetric in the first two as well as the last two, right?
Yes.
So here I'm just using for the first two. It's antisymmetric in the indices. So that's what I'm using. So it's just I could have given you this as challenge questions, but I'm just trying to tell you, like, you can, whatever expressions you have in mind, you can try to apply here, right? Similarly, the same thing here. Now you know this is, I've tried this on the last two indices in this one. Okay, so this is the challenge question. Nobody has a laptop with yours. Okay. So I was expecting some of you will have your laptop and you can try to write this down and see whether it works or not. But since you don't have, let's move on. But please try it out. Okay. Okay. So you can define Kronecker. I will give you the notebook. Why waste your storage?
Sorry.
So so you can define the Kronecker delta as well, and the syntax is delta. So some of the tests I've just given some of the tests. So you can, if the dimension is 4, you can find out what if the indices, if you keep repeated indices, what should be what it should be. You can use it to contract these vectors as well. Okay, but there's something else which is called this generalized delta function, and you can define that as well. And this is what is called the G delta, and I have just given it for just two indices, but you can define generalized delta for as many indices as you want. And you use not delta but G delta here and give the number of indices. But if you really want to know what it is in terms of if you want to expand it, you can just write expand G delta, or you can just do / expand G delta. Use that tool and it will tell you how the Kronecker delta looks like. Okay. Okay, so the next is again the Levi-Civita. So here again, this is how you are defining it, and everybody knows what a Levi-Civita tensor is? Okay.
Yes.
Yes. Okay. So when you operate it on the metric, what happens? What is this? Like it's 0, it's given here, but can you tell me why?
It's not fully anti-symmetric.
Thank you. Is that clear to everyone? Okay. Anyway, I'm not responsible for you to know all these things. I'm just helping you. Even if you don't know, you can. There's a way to know it. So I'm not sure I'm doing a lot of favor to you guys or not. But anyway, so you can. This was the other challenge question that I thought you guys can try. And this is actually interesting, to be very frank. It's not so easy to know these values. Maybe some of you know it, but you should try and find out whether. So what happens if all the 4 indices are same?
0. Even 2 of
When two of them A is going to be, then fine.
Can you prove it? So I'm talking about the last one. Is it?
No. That is not 0.
Yeah. So the last one is you should be able to say exactly what the value is.
Two indices,
When I say within this, that's a full contraction. That's even
Exactly. So what happens if it's a full contraction?
gives you
The
the
Levis.
dimension.
And there are 2, so it's a 4 cross 4, right? So it's 16.
Even if you write stuff to that becomes 16.
Do you want to do it right now? Like how you get 16? on the board.
Do
Epsilon A B C D epsilon. Ah,
You can do it? Great. See, this is what it's all about. You should try certain things.
you want to do this?
No. The last one. So I'll write it for you. So this is equal to 16. Can you prove it?
No, no.
Because
Can be written like a delta symbol expression. It is 16, but
okay. Anybody? Okay. How many of you are relativists here? Come on, you are. I have seen your CVs. Okay. The reality check hits hard. Right, so we can do metric contractions.
Or shouldn't the 4 factorial way of permutation? It should be 24.
It sh- no.
It gives minus 24. xAct is giving minus 24.
Is it minus? That depends on the definition, I think. That's 24.
so the square root of minus 3, na?
Is it? Okay, that's a good thing to check. 24, I think, yeah, maybe. Yeah, 4 factorial, yes. Okay, so you can do metric contractions. And as you can see, if you contract the metric, you're getting the delta function itself. And this gives you the dimension. Right. The last sort of operation that I wanted to show is you can also get you can also define something which is this partial derivative, and this is how the basic notation looks like. And you can use the main question that as I said, you can have multiple derivatives, you can switch accordingly. But what I wanted you guys to do is, from here, can you actually define, given this, can you actually define what a covariant derivative looks like? And if you can you then get the Lie derivative as well? Okay. Obviously, there are operations, but can you use the information that is already given to you to at least define the covariant derivative? I will give you, while I'll send the notebook, I'll give you some sort of instructions, but these are the things that you can look into. Obviously, as I said, this is not entirely what xTensor can do, but these are some of the things that we will need later in our tutorials. So I just wanted to define at least these operations. Questions? Yeah. Okay.
So when we have defined the metric, the Christopher symbols are automatically defined.
Yeah.
That's how we define covariant.
The Christopher is already given to you, right? Now, how do you define your covariant derivative? So you need partial derivative as well as the Christophers are anyway when you define you are getting the only other operation which is left was this partial derivative. So that's also given to you. So can you write your own? In principle, there is a command to get the covariant derivative, but can you write your own sort of operation given what you already know? Okay, so that is something that you can work on. And also from next time, if you have your laptop, do bring it so that these sort of things we can do it here as well. Any questions?
How to print the first program that on the Christopher symbols? Right. The first, definitely when we define the metric, all the quantities are defined, but how to print all those?
So as I said, like I gave you some example, right? So okay, let me just actually.
And how to extract Christopher symbol from the.
Oh, then what you have to do is you define your metric, and we will come to that as well. You write your GAB as what? Okay. So if you want to define a Minkowski, then you can define what a GAB is. And once you do that, then if you just write Christoffel CD, it will give you the Christoffels, which should be what? Of a Minkowski metric. Yeah. So you should get that. So that's how. Any questions? Okay. Good time to end? Thank you. Yeah, I think we are on time.
There are some questions on the chat.
There are some questions on chat. Ooh, there are a lot of questions on chat.
How many years you have Mathematica installed?
From where I can find this document. So I will, this is to Shakshi, if you can hear me. So I will anyway send the notebook, so you can go to the website, but it's called, and I have also put this at the top. So it's called xAct.es, and I've linked. This was in the initial tutorial. So as you can see, if you go here, this is where you can access the the software as well as the documentation and everything. And this is the page that I was showing initially. This is the page. So if you go to home, you can find out what are the core packages. These are the 4 core packages, but then there are the different offshoots that I was talking about. So you can look at higher order perturbation theory in GR. I was talking about this parameterized post-Newtonian formalisms. I don't know much about the others, but yeah, I mostly I had used xTensor, xCoba, Expert, and xPPN before, but that's where you can get it. Actually, let me just put this on the chat, but I will anyway share. This is in my, the link is also given, at least the URL is also given in my tutorial 0, and I will put all the links in the first tutorial as well. Voice is low. Oh, okay. That's sorted. Okay. I installed it, but it didn't work when I run Mathematica. This is a difficult problem to solve from here, but in principle, you should. I don't know which system you're using, but and this is for Roop Kiranprit. I'm not sure which OS you use, but if you are using a Linux or Unix based system, you just need to untar and put the xAct directory in the applications of your applications directory of Mathematica. So it should be in your home directory. That should in principle work. Link to the so if you just go to the website and click either on, you can just go to downloads here. So this is the one for a Mac, Linux, or any other Unix-based system, OS operating system, and this is for Windows. But if you want, you can individually also download each of the different packages, but I would advise you not to do that. Just download this entire tarball or zipped file. Installation guide is, as I said, it's given in my tutorial 0, or you can even look here in the installation notes here. So if you can click on the installation notes, this will also tell you what exactly to do. Okay. What else? You can download free Mathematica for 2 weeks. Okay. Thank you. I'm unable to install xAct on my Windows computer. I am Windows illiterate, so this will be difficult to answer. Provide direct link to download it. Excellent presentation. How is it different from xTensor? xTensor doesn't do symbolic computation. This is for if you want to go for more advanced things where you want to do symbolic computations. This is where in xTensor you have to actually specify the metric, so that's not symbolic anyway. xTensor is friendly if you are doing something trivial. Okay. I haven't seen any Python. In Python, it's generally difficult to do symbolic computations. I haven't seen an xAct for Python yet. Yeah, so I will do this. I will define a Hilbert action. Sorry, not the Hilbert. I will define an action in a different theory of gravity, and we will also get the field equations from that next week. No, for defining contravariant covariant, you just need to say which is, you have to define by this plus and minus, and that should define what is contravariant and covariant. We are taking a metric signature of -1, which is defined as the first argument in def metric. There's no, at least I don't know of any xAct package for MATLAB. It's all mostly developed for Mathematica. variation of action will be defined. Uh, If you don't have Mathematica, you have to either get access to Mathematica somehow. Yeah, Mathematica is not freely available. So, but someone mentioned that you can avail it for at least a couple of weeks. You can use it for free. Senpai. Yeah, the final question is interesting, but there are limitations. So you have to, this X core, you have to have a similar version of X core. But I'm not going to say no right away, but I feel like there are things that needs to be done in the back end for the GR calculation, the tensorial calculations to be done on Python. I haven't seen, well, Python is really good for data analysis. From a data analysis point of view, it's not, I don't think it's the best thing for symbolic. I don't know about Einstein Pi, I'm really sorry. There are, but at the level of xAct, I don't think so. So there are obviously free packages to handle simpler symbolic computations, but I think xAct does much more, and this is what we are going to see in the next few tutorials.